Any questions? Any questions on the exam homework? No? You know how to solve them? Did you get any sleep last night?
Yes.
Oh, okay. All right. Okay. What we want to do today are three things. Okay? One, we'll talk about vibrations of plates, how we model them in general, and you'll find that it is fundamentally, it will be similar to cylindrical shells, spherical shells, etc. And the second thing we'll do is how does a vibrating plate radiate sound? How do we model that? And the third thing is coupling of a fluid and a plate. Okay? As we excite, somehow, as a plate is excited, it radiates sound, but that sound radiation is a pressure that acts back on the plate. For instance, when an airplane goes by, or more severe cases, a supersonic flight, sometimes the windows will break. That's from the sound wave, actually shock wave in that case. So how does that affect the plate? So these are the three things that we want to cover today. So let me start with first the what we call in vacuum plate vibrations. And what this part means is in vacuum, meaning there's no effect of sound pressure or fluid around it. Just as if it's in vacuum, how would a plate vibrate? The equation of motion for the plate, let me first write the general equation. And then I will explain the individual terms. Okay. Here, the plate is, we would say, in X and Y plane, okay? And normal to all of that is Z, which obviously does not appear here. So if you look at the cross section, X and Y would be into the plate, into the board, or of course, we could look at the plane as it is all over the board. Eta is the plate displacement. Okay. M, rho times plate thickness, and that would be mass per unit area, where H is plate thickness. Okay. Now, here's a important quantity, B. B is called the bending modulus. And it is expressed by the following, which I'll describe in just a second. Okay, it's called the bending modulus. Yes. Normally, you have heard modulus before, Young's modulus, modulus of elasticity, it's a constant. In this case, it's a bending modulus that includes Young's modulus, elasticity, and of course Poisson's ratio, and the thickness. Okay. Now, think about this for a second. See what these all tell us. Young's modulus, cubic of the thickness. Okay. Remember Young's modulus, it's the elasticity. Okay, it determines how, it's a stiffness basically. So the same stiffness goes up by the thickness of the plate. Okay? So if you double the thickness of the plate, modulus increases, bending modulus 8 times. Okay? So these are very important relationships in that sense. Now, when we look at this, okay, when you look at this, one of the things that you can see is, okay, what does this represent? Remember, all equations tell us something, okay? What does this tell us, this term? What is that? Say again? Acceleration. Exactly. This is an acceleration, right? Displacement, double derivative. And this is some sort of a mass term. We called it mass per unit area of the plate. Well, so that's a force. And now, when you take a look at here, the whole thing must be a force also. Okay? Now, can anybody tell what this represents? The fourth derivative of displacement with respect to, say, a space, a coordinate. The first derivative gives you what? Say again? But this is with respect to x. Okay. What is the first one? Well, I mean, if you have y over x or eta over x, this is a displacement, okay? And if you take the displacement with respect to, say, the coordinate, it's a strain, it's a slope. It's a strain, slope. Make up your mind, okay? All right, and then when you go up, okay, do the engineers here remember what these are from statics? Pardon? Which moment? This one? You sure it's not this one? And What's that, the shear force? Okay, this is homework. You have to check these out, okay? All right. Please identify each one of those. Now, if we simplify this just for the sake of our study to one dimension, okay, in one dimension, then we would have okay. Yes? Question?
Can I use this equation in order to model the displacement of cutting tools?
Displacement of what?
Cutting tools.
Cutting tool. Well, I mean, what does the cutting tool represent? How do you want to represent a cutting tool?
As a beam.
Exactly, right? When you look at this, this is a two-dimensional beam, or what we would call plate. In one dimension, it acts like a beam. Okay? Of course, it depends on how wide it is, but we're now assuming that there's no vibration in the y direction. So we're just looking at one-dimensional motion, and that is a representation of a beam as well. Okay? The other things you want to be aware of is the right-hand side. Okay, everybody's writing. The right-hand side, the forcing function. Okay? Now, because this is two-dimensional, we say in space there's an x and y dependence as well as time dependence of the forcing function. Let's assume that we're exciting this with, let's move up here, with a point force. Okay? What does that mean? What's a point force? Let's say that I have a beam, or actually a plate, and I'm going to drop a ball on it, a small steel sphere. How would I model that force that's acting on it? You know this. Do you know? How would you do it? Let's say right here, someplace, you're dropping a ball. How would you do it? Well, the force itself, okay? Yes, how would you model the force? Yes, the most simple one is delta function of what? With respect to what?
X, Y, and Z. Delta X, delta Z.
Okay, what does Z do? Because there's no Z dependence on this plate.
Some Z0.
Yeah, there's no zero. I mean, there's no Z dependence, period. So you don't worry about a Z.
Then
See?
delta Y and delta X.
Yes. For this case, for the two-dimensional case, let me just go up for a second. For this case, if the point at which we're dropping the ball, then F would be represented by some amplitude, as of an amplitude, now we have to have some sort of a time dependence. Okay? If it is a true impulse, you can say delta t. Okay, and we'll get to it in just a moment, what that represents. Now, you may remember the expressions. This is amplitude 1 when x is equal to x0. Otherwise, the value is 0. Meaning, only at that point of x, it gives you a value of 1. Everywhere else, it's 0. Meaning, at that point, it's valid. Okay? And this represents the same thing. Here, we didn't say delta t minus t0 because we're assuming at time 0, it drops. Now, impact, of course, is modeled somewhat differently. It never really, in actuality, a point, or it acts as a true impulse, but there's always a finite space and a finite time during which it acts. We will not consider it right now, but it is something that we might want to look at later on. Okay? So in one dimension, as I mentioned, plate acts like a beam. Okay? So this becomes the same as a beam equation. Now, there are a couple of other parameters you should know. One of them is, now, do you remember what this expression is? Yes? No? Maybe? Emre? What is this expression? What is this? Young's modulus. What is this? Density, right? So Young's modulus is like stiffness, and density is like mass. Or is it the other way around? Yes. Okay? So this is speed of sound. But speed of sound in a material. Oops. But it's usually called the bulk speed of sound, meaning large material, three-dimensional, the way sound propagates in there. But in a plate, Young's modulus comes into play. Okay? Density of plate material. Now, in a few minutes, we will also see another type of speed. And that speed will be the speed of bending waves, how fast they travel. You don't have to write it now, but you'll see a distinct difference between a speed of sound of a material, which is exactly just a material related to the material constants, and nothing else. It's a characteristic property of the material. Okay, now, one thing we want to do is see if we can solve this problem. And to solve it, we want to be able to get rid of the differentials. And to do that, we use Fourier transforms. So how would you transform these? See, right now we have the displacement, a function of space, x, and t time. Okay? If we transform it, how would we express it? Yes? Go ahead.
Can I get the question again?
Yes. We want to transform this using Fourier transform. Okay, first of all, I want to express the transformed variable displacement. What? Kx. Uh-huh.
I'm going to transform the time also.
Yes.
And frequency double.
Omega. Omega. Okay. Now, when you look up here, do you remember how one transforms a differential? Derivative? What was it? It was very simple.
Akay over 4.
Okay, the power. So this one is a transform, but the derivative is 4th power of kx. Okay, so we have and how about here? Actually, of course, this is not just kx to the power, but ikx to the 4th, which gives you that. Okay, so let's be careful. That's what the result is. That. And here, how would we transform the inertial term? Where's the 4th power here? 2nd power, but not omega. 2nd power of I omega. Exactly. So let me just write it for completeness sake. M times I omega square. And this would, of course, go straight to a force transformation. Okay, so okay, if we simplify this, okay. One thing that we do is use the concept of impedance, as we have seen before. And impedance, again, just very quickly, is what? Yes. And more formally, how do you obtain impedance?
Pressure over speed, but
Yeah, well, in acoustic medium, it would be pressure over particle velocity. But now we have a plate, a mechanical system. Okay, so we have a force. We want to be able to divide it by the velocity of the plate. So what I want to do is express this in terms of velocity. And how do I do that? Velocity is this. Okay, this is velocity. Okay, and what I have done is pull out minus I omega from this parenthesis. So to rewrite this, okay, right, no problems here, I omega minus I omega. Let's simplify this over here. Oh. We haven't changed anything on the right hand side. Okay, now this is going to be our impedance for the plate. So simplifying that a bit further, that's plate's impedance. Let me know if there's anything that's not very clear here. Okay. In this expression, I will take this and call that KB. And KB is, KB4, sorry. Okay, where K sub B is the free bending velocity of the plate. Then we can express impedance even a little simpler. Not velocity bending wave number. Sorry. This is a number, K. Bending number. Velocity we'll get to in a moment. So KB is okay. Any questions so far? Is that reasonably clear? All right. Then, using this expression, we say equation of motion of a plate. We can express as okay. Sometimes we write it as ZP, sometimes ZB. P refers to plate, B refers to bending waves. It's no reason to get confused about them. Okay. And the in vacuum plate impedance then is okay. Let's examine this last expression a little. Okay, take a look at this impedance, and see if it's telling you anything. What are some of the things that you get from it? Number one, think about what impedance means, as I mentioned earlier. What's an impedance? It's a resistance to velocity, to motion. Okay, so what does it all say? You can look at, there are three terms in here, okay? And when you look at those, they will tell you something. Yes? There's an inertial term, okay?
Changes wavelength.
Changes with the wavelength, that's correct. Mm-hmm.
I think it's about the characteristic of the plate, because if the 1 minus part was 1, it was like a rigid plate.
Mm-hmm.
But there's a ratio in KB. It's
Mm-hmm.
like the characteristic of the plate, so the
Okay. Well, okay. That's these are all in the right direction and very good. Now let's take a look at these. If, for one reason or another, I will explain how that might happen. If kx were equal to 0, okay, kx were equal to 0, then what do you have? You have minus I omega m. We talked about this before. What's an I omega m?
Mass impedance.
Exactly. It's just an inertial impedance, a mass impedance, and there's nothing else. So it's just the motion of a mass that's moving. See, if you, I would always do these. See, you can write this as minus I omega m x dot. That's the same expression as this, right? Because I omega x dot is acceleration. Okay, so this, in this case, the inertia of the mass. And so think about it. Now, what is the condition under which kx would be 0? What does that mean? What's kx? It's a wave number that comes from Fourier transform. Okay, in this case, it really is part of the forcing function. So what is k as a wave number? It's omega over c, or 2 pi over lambda. Okay, let's look at this relationship for a moment. If kx is 2 pi over lambda x, lambda meaning the wavelength, kx equals 0 mean lambda x is equal to infinity. Okay, so there's really no vibration in the spatial domain. It could move as a flat surface, as you said, rigid, okay? But that's it. So it's very long, flat piece that's moving up and down. That's what it means. All right. Now, what else can we say? What happens, what does it mean? Kx is equal to Kb. Now, what is Kb? We said Kb is the free bending number of the plate, okay? And it depends on its mass per unit area, meaning density, and bending modulus, okay? Yes, and bending modulus. So what can we say anything about this? And then what it means for these two to be equal without going into detail. If the ratio here is equal to 1, what happens? Say again? Yeah. Okay, but when impedance is 0, under what conditions it becomes 0, or what does it correspond to? Think about a single degree of freedom system. When the impedance is 0, what happens to it? Say again? In the electrical terms, yes, resonance. It's a resonance condition. Okay? But in this case, we're not really talking about a frequency resonance. We're talking about wave numbers or wavelength. So it's what we call a spatial resonance. I'll try to explain what that is. This means a spatial resonance. Now, coming back to this just for a moment. Okay, write it down. Now, coming back to this for a moment. There's a relationship between frequency and bending wave number. So at a given, if you're exciting a plate with a particular frequency, it has its own natural bending wavelength. Okay? It just, when you have a string and then you're shaking it at a frequency, it develops a particular wavelength. Similar in concept with the plate. There's a frequency and wavelength relationship. But this Kx comes from the forcing. Okay? The force that comes onto a plate has its own distribution, wavelength distribution. If that wavelength distribution and the free bending wavelength correspond, then you have a resonance. It really then vibrates immensely. Impedance goes to 0. That's what it means. Hopefully this will become more clear as we see other examples in the future. At first, this is very difficult because you have probably only heard about resonance in terms of frequency, time frequency. But this is a spatial thing, which is a little bit different than what you're familiar with. Okay. Let's take this for a moment. And look at the same relationship here. Okay, but in this case, omega divided by CB. B being bending wavelength. Okay, this is a bending wave number associated with a frequency, but wave number is always a ratio of omega, frequency, to a speed. Okay, speed of sound, speed of whatever it is that we're measuring. Of course, same thing is true. It's also equal to 2 pi over the wavelength. Now, in our case, omega over CB, okay, if we write the equivalent value what this does is, this gives us the expression for the speed with which the bending waves travel. Okay. If we pull it out of here, now, let me just remind you for a moment, everyone, the speed of sound in a material, in a plate. There's a fundamental difference between these and the bending wave speed. And what is that very fundamental difference? And these. Exactly. Bending wave speed depends on frequency. When a speed depends on frequency, we call that dispersive. Okay? Bending wave speed depends on frequency. And physically, just imagine what that means. One thing is, I don't know, maybe quarter-inch thick beam. Nobody's writing. Okay, just look up for a second. About quarter-inch thick beam, maybe that wide, and from here to the wall, hanging on just some strings, just freely. I describe because I have seen this, okay? If you do, give it a pulse, okay? Bending waves will go, come back. And you'll hear distinctly different sounds coming back at different times. Why is that? Because the high frequencies travel faster. Okay? Makes sense, right? 1,000 hertz or let's say 10,000 hertz will travel 100 times as fast as maybe a hertz. Okay? And so the low frequencies come back later. Lower frequency sounds on the plate. And so this is very interesting and important. Why is that? We'll see in a moment. When a beam or a plate is vibrating, they have to travel faster than speed of sound in air to be able to radiate. So only high frequencies radiate as much rather than low frequencies when a plate is vibrating. Okay? So this is a dispersive relationship that depends on the frequency of sound. Frequency of vibrations. Well, in these expressions, we did not see any influence or any potential effect of damping. But we know that all materials have a certain amount of damping in them. Have you seen before how would you go ahead and include damping in the system? Because we're saying here, if Kx is equal to Kb, then you have impedance going to 0, and so there's a spatial resonance. But there has to be damping in the system. Where would damping come from? Let's think about material damping, because that's what all the materials have. Effects of damping. In this case, let's make sure we are clear about damping. There are, of course, all sorts of mechanisms of damping, okay? What does damping mean? How do you understand damping? Khan? It's a resistor. What does the resistor do? It dissipates energy. In electrical terms, how does it do that? Into heat. Converts electrical energy into heat. How about in mechanical terms? What's dissipation? What's damping? You know it. Come on.
It's dependent on velocity and...
No, but I'm not. My question is, what does it depend? What is it? What's damping? Damping is, if you have damping in a system, what does it do? Let's say a vibrating system, you put damping in it.
It absorbs energy.
Right. And what does it do with that energy? Does it store it in a bank?
Probably turns it into heat.
Exactly. Okay. That's the fundamental mechanism of damping. It dissipates an ordered energy into disordered energy. By disordered, I mean molecules that absorb that kinetic energy that's normally a usable energy into thermalized motion of molecules, whether it's in fluid like viscosity or in a solid that becomes warmer. As you bend the wire, just think about it. That's exactly what you're doing. You're putting energy into the molecules that makes it hot. And that you cannot recover. That's why it's a dissipation. You cannot use it anymore. Well, you can say, if I do a lot, I can boil water, but not really. I mean, maybe. Okay. So the mechanism is, it's a dissipation of energy. And there are a number of different ways of doing this, or number of different damping mechanisms that exist. Joints, for example, when two surfaces touch one another, or using polymeric materials. If this is like a thin plate and it's vibrating, you can put a polymeric damping material and so on. But any given material has some amount of damping or dissipation mechanism in it. And the way we model it is, again, these are approximate, but we take the Young's modulus, okay, and we express it as a complex variable. And the way to do that is Young's modulus 1 minus some sort of a damping factor or loss factor, where delta is called a loss factor. It's usually, for most materials, it's 1%, 10 to the minus 2. Most materials, using that value usually gives you a reasonable estimate for metals. Now, if we start with the Young's modulus, where does Young's modulus appear in our equations? In the bending modulus. So that means bending modulus goes to and becomes a complex value. And in fact, we can say, because it's directly proportional to Young's modulus. And in this case, the plate impedance expression what we have done is taken the normal plate equation of motion in terms of impedance and made the bending modulus a complex number. Now, if we expand on that, oh, I shouldn't have erased that. If we expand on that, then we have okay. What you see now is an additional term in the impedance. Okay. If you go back and look at the ordinary single degree of freedom system vibration equation, you'll see something very similar to this. Okay? The resonance part and the damping part. Okay, if you look at the impedance expression for a single degree of freedom oscillator, you'll see a similar expression. Now, what we do see is by making kx, this is of course by making them equal, you really never get zero. So in this expression, you do not have a zero value for impedance unless the loss factor is completely absent. Okay, this is the way to express damping in plates or beams, for that matter. Any questions on the plate vibrations? Nothing? So you know how to write. Let me just pull this up for a second. You know how to write the equation, bending modulus times the fourth derivative of the displacement together is a force per unit area. We have a force per unit area due to plate inertia and a force per unit area that's acting on it. What's a force per unit area? It's a pressure, okay, acting on it. And to solve this, an easy way is to express everything in the Fourier domain, and then we have an impedance expression. This is without any damping in the system. This is with damping in the system. And then we did an examination of what it means for the plate to be in spatial resonance, and also the bending waves being frequency dependent, the speed of bending waves being frequency dependent. Okay, let's take a 2-3 minute break.